Okay, we can start soon. How many people? Okay, there are some waiting still. Okay, I think we can start. Although on the list there were much more people, but perhaps they will join us later. Okay, my name is Gregorz Nowak, as you already know, probably. With some of you we have already met during your studies, with some, of course, not. And we'll have together the lecture on thermal stresses. So I'll try to give you some brief information on the topic, on the thermal stresses, which is quite important in industry, in machinery, especially where we have to deal with temperature changes. We have 15 hours altogether of this lecture. So as you saw, it's divided into 4 weeks. So in this time we should cover the entire area I wanted to discuss with you. So probably everything will be set. Some people coming. I have given you the code that you can enroll yourself and not waiting for my acceptance, but unfortunately most of you are waiting for acceptance, not using the code. Nevertheless, okay, so there's a lot of people already. I think others will still be coming. Not to losing time, I'm going to start with the lecture. Wait a moment. Okay. There will be the. Okay, can you see the presentation?
Yes, we can see.
Okay, that's fine. Okay, I know that there are some problems. I'm recording this this lecture, so it will be available here on Teams in this channel, in this course, because as far as I know, there are some people that still don't have the account, or the university account. The email address, and they cannot contact or they cannot enroll to the course. So I don't know why it is so, but it is. So this will be, as I said, it will be stored. As far as I know, it is stored for about 20 days or something like this. Then it is automatically cancelled. So if you need some information, please look at this. You can return to the lecture or to a specific area of this lecture. I will also provide the presentation, so the slides which are used here on the platforma. So there will be PDFs of this presentation, so you can make use of that. Okay, so let's go. There are some materials available. There are some books which cover the area of thermal stresses. As when you
excuse me,
yep.
I do not see a presentation.
Is anyone else that does not see the presentation? No, I don't know what's going on, but you should see it because I'm sharing the screen or sharing the presentation. Do other people see the presentation?
Yes, we can see.
Yes.
I can see the
We can
presentation.
see it.
Yeah,
So,
it's okay for us.
I don't know. I don't know what's going on. It must be something on your side. Okay, so there are several books, generally more or less defined as thermal stresses, different, and more or less they cover the same area from different point of views. Usually, most of these information are the same. I'm using the lecture is mainly based on the design for thermal stresses. This is the left-hand side position here. Design for thermal stresses. Boron. The authors. There are also other books. Once I don't know now, but once I found a PDF, a free PDF of the thermal stresses, design for thermal stresses. So you can check to find it. Probably you'll have a book where you can a handbook which can be used to deepen your knowledge or satisfy your curiosity in this area. But anyone is good enough if it's easy to be understood or easy to be read. It's okay. So I have a preferred book. Any of them is good. I'm using that one, the thermal stresses. Can you also see the pointer, the arrow?
Yeah, we can see it.
Yes.
All right. Okay, so we can proceed with the basic information. I'd say that in general, we'll discuss the thermal elasticity. So we will be in the range of thermal stresses which are within the Hooke's law region. You may remember from your strength of material, mechanics of material course, that at some range of loading, there is the Hooke's law valid, which means that stress and strain, so the formations and the cause of the formation, so the loading, they are proportional. So it's a straight line between those two quantities. But it is so up to a certain value of stress, which is the yield stress. At this point, so when we surpass this value, material starts to behave plastically, so it exhibits plastic deformation, and this dependence is not anymore linear. So the Hooke's law is not valid there. Usually, stresses above yield stress are not allowed in structures unless this is a, let's say, technological process, and you try to shape a body. You need to go into the plastic deformations, but we won't talk about this area of plastic deformation. So we will be in the area of thermoelasticity, which means that stresses are within such a range that Hooke's law is fulfilled. So stress and strain. Strain means the deformation, relative elongation, let's say, of a body, of a material. So those two quantities are at linear dependence to each other. And the thermoelasticity, or the deformation and stresses which occur in such a case are caused by temperature field. So we have some changes in temperature field, and this is the reason for material deformation. As you may have encountered that phenomenon in from autopsy. You probably saw deformations of bodies due to changes in temperature. In general, thermal stresses which are caused by temperature change, the thermal stresses arise in a system, in a component object, when it undergoes a change in temperature. This is one thing which is required, which is crucial. And the other is that the component, system, or element, or whatever, is mechanically constrained. So it cannot freely expand. So due to temperature change, it would like to extend, change dimensions, for example, but it is not possible, or it's only partially possible, or completely impossible because of constraints which are imposed on the body. We'll discuss in a moment what the constraints can be and what is the reason for different stresses. So the topic will be here covered during this lecture. I'm going to give you the information on the most, let's say, common cases and the basics ones, because if we are going deep and deep into the material, it starts to be quite complex. So firstly, we'll start with with some information on the behavior, on the phenomena, and then we'll try to discuss quite simple cases, so one-dimensional cases on the basis of bars, for example, which undergo deformations, and as a consequence stresses which can occur there. And then we'll try to a little bit extend it to shells, and so two-dimensional objects, and disks and shafts, which are the most common objects encountered in industry or in machinery. So generally in machinery, so which may be of interest. Of course, we will discuss it theoretically. I will show you some dependencies, how to estimate along the thermal deformations, how to estimate thermal stresses. But in general, nowadays we are using computer programs, advanced computer systems, for example, ANSYS or other similar systems, which cover this topic as well. But I'm trying to give you some knowledge on this topic, on the interpretation of results, and on what is important there. Because, as you may know, the program will not do it itself. You have to provide some information, put some data in, put the boundary conditions, supports, and so on and so forth, and you obtain result. And you have to be able to interpret this result, because if you put rubbish in, at the end you will get rubbish, and you have to be able to interpret whether the result is physically possible, whether it is probable, or completely rubbish. So this is that's why we will discuss here different topics from the, let's say, basics point of view, just to give you overview how should it work and how to use this information. Okay, so here we have two situations. One, body, let's say a bar, can freely expand. So when we observe temperature change, it may be a temperature rise or temperature drop. Doesn't matter. The object starts to expand. And if there is no constraints, no restraints against the formation, and the body can freely expand, so there is nothing that constrains the deformation, the body will extend or will deform, and that's it. So nothing else will happen. Apart from deformation observed, which can be measured, no stress will occur. But on the other hand, when we have our object, the same object, supported somehow, let's say it is constrained due to walls. So we have a straight bar of a given length, and it is placed between walls, rigid walls. Rigid means that they do not deform at all. Whatever the force is, they do not deform. Someone is unmuted and does some disturbances, so please mute yourself unless you would like to ask something. Okay, so we have a bar which is, let's say, at given temperature, it's at stress-free condition. So it is perfectly adjusted to the distance between the two walls. And then we try to change temperature. Let's say we heat it up a little bit. What happens? The material tends to extend, but the walls do not allow for the extension. So the material presses against the walls. On the basis of the third Newton law, the walls revenge the same. So they provide a reaction to the deformation of the body. And you can imagine that it seems that the object is compressed with the walls. So in general, the thermal stresses are actually mechanical stresses resulting from forces caused by part attempting to expand or contract when it is constrained. And here we have the constraints, the two possible types of constraints which can occur in such a situation. One are the internal constraints, the other are external constraints. Internal constraints are restraints present within the material, inside the material, because the material expands or contracts by different amounts in various locations. So you may imagine that the higher the temperature or the lower the temperature, with the temperature change, material expands. And when part of the material, this is the description is reversed. So let's say we have this situation. We have a pipe with hot gas inside, and outside there is a cold water. So look at this, what happens here. The material, the pipe, it's hot here and cold here. So it tries to extend at the inner surface, but the cold water does not allow for extension of the external surface. So there is a conflict within the material between the areas which are hotter and areas that are colder. And inside the material, a stress occurs. So mutual interaction between the hotter and colder parts. So this happens, everything happens inside the material. External constraints are those that act on the entire system from exterior, and they prevent expansion or contraction of the system. Let's say this is the situation we have already discussed a moment ago. So we have a bar between two rigid walls. They do not necessarily to be rigid, but for now, let's assume they are rigid. So they do not deform, they do not move at all, whatever the force is. And they do not allow to expand or contract for the bar. So very often we have both of them together. Sometimes we can have only one of them. Let's say usually external constraint is observed because we have to if we build an object, system, a structure, whatever it is somehow mounted to the foundations. It cooperates. It is connected with other objects. So there are restraints resulting from the support. Of course, they may be more or less stiff, so stronger or weaker, let's say. If the system exhibits a non-uniform temperature distribution within the material, let's say as it is shown here, it can also have internal constraints. So if the material is uniformly heated up or cooled down, so the temperature is exactly the same at, of course it can change, but it changes in the same rate at every point in the material. So we heat it up or cool it down equally everywhere with the same rate. We will not have the internal constraints. But if the material is not uniformly heated up or cooled down, and we obtain a distribution of temperature in the material, also internal constraints can occur. So we'll discuss both cases. We'll discuss how deeply the constraints affect stresses and how we are able, while designing the system, for example, how we are able to release them a little bit. It is not always possible to get rid of thermal stresses at all. They will be, but we have to have control on them. So this is we'll discuss how to control the stresses, or how to predict what is the magnitude of stresses that can occur there. Okay. And here you have some situations where the stresses are observed. For example, here you have railways, and if they are quite long, there are no gaps between them, and let's say they were assembled during, let's say, winter, during cold times, and there's quite a long distance of continuous railway, and there is a, let's say, summer. The temperature has risen significantly, so you can see what can happen. It is not on purpose such a slalom made. It's just a result of thermal expansion of the railways. So you see, the result can be a little bit destructive. Same story if you have bridges, for example, for cars, for trains, whatever. We do not fix them to the foundations, to the surrounding grounds. Why? Because the bridge also expands. It contracts or expands. So you can encounter on the road such things. There's a gap between, let's say, the bridge and the ground. And to some extent, the bridge can expand or contract. So there is such a cover, let's say a metal cover, which covers the, let's say the gap, but it allows to a certain deformation. If there is no such a thing, if you build such a bridge during summer, on winter it will be inside the river, and opposite. So the thermal deformations would destroy it. What you can also see on the foundations, there are some rollers. So the bridges are not fixed. As I told you, there are usually such rolls that it can expand, so it can slightly move left, right, so contract or expand during temperature changes. So this is the idea that we prevent destruction, for example, of such object. Or we have piping system. If there is a hot water, for example, or a steam transferred for district heating, we do not use straight lines for many kilometers, because again, changes of temperature would destroy it. So would provide buckling, the same story as here, or it would be broken. So we do such bellows that allow some compensation of the thermal expansion. You can also observe the thermal expansion, contraction on the electric wires, especially the high voltage wires. They are quite loose in summer. They are more stretched in winter, and you can observe how they hang from the supports. These are the situations. Especially, this is very important when the temperature changes are quite significant. So the amount of how deeply the temperature changes, and be sure that there is no the reason of a given temperature. If the temperature does not change, it doesn't matter what it is, what the temperature is. The temperature must change, and how deeply it changes, the bigger the deformations will be. If the deformations are constrained, we develop stresses in the material of the object. Okay, we usually use different models to describe what happens in particular objects. As you may remember from your let's say mechanics course or mechanics of materials, so strength of material courses, we usually use some models of objects which are bar or beam, so one-dimensional object, which are, let's say, pressure vessels, so shells usually, some discs. So most common objects encountered in practical applications, and they may be, of course, three-dimensional objects, which are quite difficult to be analyzed by means of a sheet of paper and a pencil. So in such cases, you really do not have ready formulas for stress development, rather than use specified software to determine stresses in such cases. The determination of thermal stresses is usually it follows the thermal determination, or the determination of thermal field. So firstly, you need to determine the temperature distribution within the object, whether it's a steady state or a transient state. And on this basis, on the basis of temperature distribution, temperature field within the object, you can calculate thermal stresses. So these two phenomena are usually connected to each other. So for many calculations, the first thing you need to do is to determine thermal field, and on this basis, with application of the appropriate material properties and application of constraints, you obtain deformations and stresses. So I'm just giving you a brief revision. I'm not going to cover the topic of heat transfer, but just a brief information and what we need to provide for usual computer system or the system you can write yourself, what we need to provide to get the temperature distribution, and then what to do to get the thermal stresses. So in general, the thermal field is governed with the Fourier equation, where the heat flux is proportional to the temperature distribution in the body. And here we have the basic equation, which is the Fourier equation, that the heat flux is the heat conduction coefficient and the thermal gradient. So the distribution in temperature in a body. So experience, so I mean the physical observation, suggests that two things about the heat flow that result from temperature non-uniformities in a body are the Q, which means the heat flux, and temperature gradient are exactly opposite to one another. And the magnitude of the heat flux is directly proportional to the temperature gradient. So here we have one of the material properties, which is the thermal conductivity. Of course, this is a vector quantity, so it can be resolved into components in X, Y, and Z direction. If we take into account the transient conditions, the equation, which is called the diffusion equation, heat diffusion equation, consists of a Laplacian of temperature, the factor, the time factor of temperature changes, and some coefficients, some material properties which are involved. So this is the C, which is the thermal capacity, there is the rho, so density, and the thermal conductivity, which is usually gathered together in one coefficient, which is the thermal diffusivity. So this is the equation for unsteady states. We'll usually cover here the topic of steady states, or let's say a snapshot of unsteady states. So when the unsteady state happens and we can have a temperature distribution across a body. But we will not discuss the problem here. We will not solve problems of unsteady, so transient cases, because it's quite difficult to be solved on a sheet of paper apart from simple cases. These are the stories that are solved usually with a computer program, the software. If we have the steady state, the Laplacian of temperature is 0, so the second derivative over the space coordinates is 0. To solve the equation, this is of course the differential equation. We need some conditions so that we know something about the field. If the problem is transient, so we have to foresee how an object will be heated up or cooled down, so how the temperature changes in time. We have to know what happens at some instant of time, let's say at the initial time of our computation. So we have to provide initial condition. So let's say a temperature distribution, for example, at t equals to 0, for example. So at the beginning of our computations, or any other case, but usually is the initial condition as the case where we know something about the thermal field, and then it evolves somehow on the basis of further conditions which are applied there. We can observe how the temperature, the temperature field changes during with time, and we additionally need to provide thermal boundary conditions for the solution of the equation. So there are, as most of you knows it well, we have 4 kinds of boundary conditions, 4 possible boundary conditions to be specified. All of them work well with the equation, of course. Not all of them are easy to be obtained for real situations, or sometimes not all of them are equally good applicable in the numerical software. Some are, let's say, more problematic than the others. But this is the problem of temperature field solution. So the first boundary conditions can be that we know how temperature changes at some specific points, line, surface, whatever. It can be changed in time, or it can be constant in time. So if we have transient conditions, it will change in time. If we have steady conditions, it will be constant during the entire time of our calculations. But one possibility is to provide temperature at some locations, some specific locations. The other possibility is to provide heat flux on a given surface. So according to the Fourier equation, we can calculate the temperature distribution within the body. So this is the second possibility. The third possibility is when we have contact of solid body with usually a liquid or a gaseous body, so with fluid. So we have a solid body and we have a fluid on one side. That can be fluid on both sides, whatever. On the boundary between those two domains, the fluid and the solid one, there is of course an equality of heat flux transferred through the boundary, but we usually determine it as a coefficient of convection, so convective heat transfer coefficient, denoted here as alpha, and temperature difference between wall of the solid body and temperature of the fluid. On one side or both sides, doesn't matter. This is the condition which is most often encountered in real life, in the real conditions. We usually have it, and it works quite well with the numerical software also. So this is very, very often used. And the fourth one is the contact condition, when we have bodies that are in contact. So we can equalize the heat flux that leaves one body, enters the second body. So we have temperature connection here on this. We can have a temperature connection on the. They can be the same depending on the condition here on the boundary, but generally what leaves one body enters the second body. So this is the four boundary conditions, and there are the four possibilities which are usually used to solve the heat conduction equation and to determine the temperature field. And then we switch to a mechanical part. So we already have somehow determined the thermal field, and we try to get into the mechanical field now. So we'll discuss some issues on the mechanical problem. First, we'll start with the main properties that affect the material behavior under the changing temperature field. So let's start with the thermal expansion. It can be, of course, a revision because this topic should have been somewhere before in your education, so on physics courses, on strength of material courses. But to have, let's say, to recall the information, we'll discuss it a little bit. So, for example, if we have a bar, a rod, whatever it is, a body, in temperature T1, and it has length L. So if we heat it up or cool it down, so generally we change the temperature, the body will expand. We can discuss generally two thermal expansion coefficients, two possibilities or two ways of discussing the thermal expansion. One will be changes in linear direction, so linear changes in dimensions of the object, or the volumetric expansion. The linear coefficient determines how deeply, to what extent the material will expand if it's heated up or cooled down. Of course, this is schematically shown that we heat it up. Of course, if we put fire here, it would be not that easy as it looks like here. In general, we assume here that the object is uniformly heated. So at a given instant of time, in each point of the body, we have the same temperature. So it could not be heated up like here with the fire, because some more complex phenomena will occur. We will discuss them a little bit later during our course. But it just, let's say, a schematic marking that this object is heated up. So it extends by delta LT. So the temperature changed, and we observe a change in length of the object, and it is denoted by delta LT. So elongation, thermal elongation. And it will be the case if the object has possibility to elongate. The linear thermal expansion coefficient, as it is defined here, as you see, 1 over L dL over dt. What it means? It is a fractional change in length, because here we have change in length divided by the original length. So this is the, let's say, relative elongation, in other words, strain, per unit change in temperature. So this is the unit change in temperature, while the stress in material is kept constant. So this is the marking sigma here. So we usually measure or determine the linear thermal expansion coefficients for thermal stresses. Usually it is measured while thermal stress is 0. This is the usual case of determination or measurement of the linear thermal expansion coefficient. So you see dL over dt. So increase in length due to increase in temperature, and this is divided by the initial length of the object. If there is no possibility to extend, as I've already shown, the material tends to extend. It would do that by delta T, but if there are walls, there are constraints, it is not possible to move. So to keep it in unchanged length, a force must be exerted from the constraints. And this is the reason why stresses in the material occur. This is the linear coefficient, so we observe changes in length, in particular direction, how the object changes in its linear dimensions. We can also observe it as far as the volume is concerned. So we have an object, three-dimensional object, and we change its temperature. It will change the volume as well. So each dimension changes or may change. And in such a case, we can determine, let's say, volumetric thermal expansion coefficient, which is of course not independent on the linear thermal coefficient, but as we see, each the object change its linear dimension in each direction. So there must be some connection between them. But in general, we define the volumetric thermal expansion coefficient, here beta T, as 1 over V, so volume, times dV over dt at P. What it means? The volumetric thermal expansion coefficient is the fractional change in volume. This is the fractional change in volume. Change in volume divided by the original size of the object, by the original volume, per unit change in temperature. While the pressure, so stresses from around, this is usually called the compressive stresses from around, is usually called as we do in liquids or in fluids. So pressure, just a pressure, these are the normal stresses compressing the body. In other words, these are hydrostatic stresses. So for constant P, we calculate, we determine the volumetric thermal expansion coefficient. So how the volume changes if we change the temperature, let's say by 1 Kelvin, for example. If the material is isotropic, which means that we have the same properties in all directions. This is the most common case we discussed. The two thermal coefficients fulfill such a equality. So the volumetric one is 3 times the linear one, which is quite obvious because the material expands in each direction, as we have 3 of them in each direction in the same manner. Okay, so this is the one of the main material properties that affect the thermal deformation. We see that the bigger the temperature change, the bigger the change in the object size, either volume or the linear dimension. If we discuss, let's say, object, one-dimensional object, so we treat only changes in stresses in one direction. Okay. Let's look at some other quantities. If we have a, let's say, bar which has a length x0 and the width y0 and let's say lateral direction, and we apply force, so this is just a mechanical action, it changes also its size due to the action of force, due to the deformations that occur in the material. Of course, this is not observed when you discuss pure mechanics. So if you are recall your mechanics course, there was no deformation at all. So we dealt there with rigid body, so body that does not deform, which is, let's say, artificial one. In a course of mechanics of materials, strength of materials, we assume that the material deforms, which is the case in real life, and the deformations, although are quite small, but they are. So if we, let's say, apply force to the bar, it changes its dimensions. And we can determine here strain, which is denoted with epsilon in x direction, for example, in this direction. So this elongation in this case is du over dx. Du means change in length, unitary change in length. So looking at the entire body, it is change in length, so this elongation divided by the original length. Of course, it's a little bit more complex. We have to do it on infinitesimal elements, but please recall to the strength of material course, and you have it determined more precisely. In general, this is the du over the dx, so elongation of an infinitely thin piece of material. So in general, this is the elongation divided by the original length. And this is axial strain, means along axis of the body. And we see that it elongated. But what we also see, it contracted a little bit. So we observe lateral strain in y direction, but also perpendicular to the screen in z direction. And they are calculated in the same way. It's dv over dy. uv and w are displacement. So how far the material displaced, how far it moved. So we observe that formally at the beginning, the height of the bar, let's say, was y0, and now after application of force, it changed to y1. It diminished in this case. Similarly, will be in the z direction, which is quite obvious. And on this basis, we can determine here a Poisson's ratio, which is the ratio of lateral and axial strain. So along, let's say, perpendicular to the action of force divided by the strain along the force. There is a minus sign because if epsilon x is positive, so the body elongates, the lateral strain is negative. It contracts. Opposite, if we compress the object, so it would be shorter, so epsilon would be negative, y and z would be positive because it would be thicker. So they are always opposite in sign. To have a coefficient positive, there is a minus sign introduced. So a Poisson's ratio, which shows us one of the main material properties of the object. And so this is the we encountered this property previously in our strength of material course. So it's just again a small revision. Here you have the behavior of material. Usually, let's say the initial part of the stress strain curve, which shows us the material behavior. We have here the cause for deformation and the deformation. So strain, stress. Let's look at these only. So the epsilon x and sigma, which is of course force divided by the cross-sectional area. So the normal stress, the elongation stress. We see that at the initial part, starting from zero stress up to a certain point, a certain amount of stresses, certain magnitude of stress, we observe here a straight line. This straight line, the angle of the straight line is determined on the basis of so-called Young's modulus. Young's modulus is nothing else, as you see, we have loading and we have response from the material in a form of deformation. So it shows us the magnitude of Young's modulus, which is exactly, as you look here, d sigma over d epsilon. So in other words, this is tangent of the angle. This is Young's modulus. Shows us the dependence, how material reacts on stresses. So how elastic the material is, or how prone to deformation it is. If we have big Young modulus, so very steep curve here, it means that big stress results in small deformation. Otherwise, if we have small Young modulus, you don't need to put a lot of effort to deform the body. So let's say we have a steel, and the Young's modulus can be about 200 gigapascals, and you can have a sponge where the Young's modulus, I don't know, several pascals or several kilopascals. So huge range in difference. So it generally says us how prone to deformation material is. It is usually determined at steady, at constant temperature. So we have here a derivative of stress over strain, but in general it can be quite easily measured. You also have done it, or you did it on your strength of material course on the labs. There was so an exercise that you determined stresses. You determined on the basis of this stress strain curve. So this material characteristic, you determined Young's modulus as the angle of the initial part, tangent of the angle of at the initial part of the stress strain curve. There are also some additional coefficients, but we'll discuss it in a moment. So these are the quantities which will be here discussed and often used. So epsilon, Young's modulus, and sigma is the normal stress. We also have shear stress, but it will appear a little bit later in our course. So this is the normal stress, in other words, perpendicular to the surface stress. The shear stress is in the parallel direction, so parallel to the force, for example. Okay. And here you have some, let's say, data for most common materials. For Polish people, it's nothing new. For people that are from abroad, that may be something new for you. RE. This is the ultimate stress, which is usually in British literature denoted by sigma U. This is ultimate stress, so the maximum stress that material can survive. RE is the yield stress, usually in, again, English books denoted as sigma Y. So this is the onset of plastic deformation, and this is the maximum stress on the stress strain curve, the engineering stress strain curve. Rho is, of course, density of the material. E as the Young's modulus in gigapascal expressed. Nu is the Poisson's ratio, or the Poisson's coefficient. And alpha is the linear expansion coefficient. It's this value times 10 to the minus 6 power. As you recall, I haven't told that the unit is 1 over k, but you should have in mind what it means. If we come back to the coefficient, look here, it's delta or del dl over dt and divided by L. So to be honest, the actual unit should be, let's say, millimeter or meter, but meter is big, so millimeter divided by millimeter divided by Kelvin, so by change in temperature. So millimeter over millimeter, you can encounter such description in some books because it shows us the physical meaning of this quantity. This is strain. So change divided by the original quantity. So change in length divided by the original length. So in general, the final result, if you cancel out the millimeters or meters, whatever it is, it's 1 over k. But you have to have in mind that this is the, let's say, strain resulted from change in unitary change in temperature. So these are the magnitudes of alpha, so linear expansion coefficient, and here we have additionally the thermal diffusion, which we'll discuss a little bit in a moment. So some properties, if you do some computations, you can make use of these quantities. You see how do they change, what is the amount of maximum the ultimate stress, depending on the material. It can be quite high, let's say above 1000, but it can be as low as, let's say, 100 for aluminium, depending on the material, or cast iron yield stress as well. There are some materials that do not exhibit yielding because these materials are brittle materials. So we have ductile materials that exhibit plastic deformation. We have brittle materials that do not exhibit any plasticity, only elastic deformations and breakage, rupture. And we have a mixture, so elastoplastic materials, which are a little bit, they are not brittle, they are elastic to some region, and then they exhibit a plastic deformation. So these two here, in this case, cast iron is the material that exhibit no yielding, no plastic deformation. Okay. So you see, depending on how big the thermal expansion coefficient is, that big will be the reaction of the material to changes in temperature. But it is quite small amount, as you see, times to the -6 power. Okay, let's look at the same story but in 3D. We have a three-dimensional bar whose volume is, let's say, V0 is lab, but it is a length, height, and width. So this is the initial volume. And if we apply force there, P, we obtain the deformed volume. Will deform, so the deformation can be described so that the new volume will be L plus epsilon x times L. Of course, this is elongation. This is delta L in x direction. This is delta A, and this is delta B. So change in dimension in particular direction. So this is the deformed case, yes. And So we can introducing here the nu, so the Poisson's ratio. So substituting epsilon y with nu epsilon x, and same for z direction. We can transform it to this form, so L times A times B, so the V0, and 1 plus epsilon x times 1 minus nu epsilon x times 1 minus nu epsilon x. Minus because there is a contraction in these two directions, so z and y. So it can be written, if we simplify it a little bit or we expand it, it may be written in such a form. So here we have the V0, 1 over epsilon x, and some other fractions. And we can observe that the fractional change in volume may be found, as it is shown here, where we have omitted this factor here. There's still a multiplication here, so there will be epsilon squared and epsilon to the third power, since these are very small quantities, and small quantity squared or rise to the third power, it's very, very small. So these terms are unimportant, so they are negligible small. And we can say that the fractional change in volume can be expressed, of course, as a change in volume. So V1 minus V0 divided by the original volume, V0, and it is epsilon times 1 minus 2 nu. And what we can observe here, that for homogeneous and isotropic material, the value of Poisson's ratio is between 0 and half. So 1 second, half. Look at this. If the Poisson's ratio were greater than half, a pressure applied on the body would cause the volume of the material to increase. You see, that negative part would be greater than 1. Which is, of course, not observed in engineering materials. If we take the material, the boundary value, so half for nu, the volume does not change as the tensile or compressive force is applied, whatever the magnitude would be. So that would be the boundary value for, let's say, perfectly rigid material. But in general, this is below half, and it's for many material it's 1/3 for many, as you saw in the table. Some additional modules that can be encountered apart from the Young's modulus. This is the modulus of elasticity in shear. In other words, shear modulus. And it is defined as the ratio of the shearing stress, generally, to the shear strain, resulting from the Hooke's law. And the shear modulus and Young modulus are related to each other, so they are not independent, and they are connected together with use of the Poisson's ratio. So here you can see this. The shear modulus. So it shows us how the material deforms under the distortion of the material, so changing in shape. Elastic modulus, the Young's modulus, shows us how material deforms, how the linear dimensions change. But the shear modulus, which is, in other words, defined as the Kirchhoff modulus. This is Kirchhoff modulus. Very often you can encounter this name. It shows us how prone is the material for shear deformation, so for changing in shape. And the shear modulus and Young modulus is connected with together with use of the Poisson's ratio. So in general, you need to know these two quantities, which are quite easily to be measured, as you may remember from your, again, strength of material course. They are measured in the tensile test. Both can be determined, and if you know these two, you don't have to bother how to determine G, how to determine the shear modulus. It can be easily calculated. If the material has a Poisson's ratio of 1/3, which is very much the case, for example, steels, the shear modulus will be 3/8 of 8 of E. So if you put here 1/3, you can easily recalculate it. We can also define a bulk modulus, which is, of course, as the measure of volume change of a material. This is done, so isothermal bulk modulus, sometimes referred to as Helmholtz modulus, from the name of the, let's say, scientists who determined it, is defined as the change in pressure per unit volume strain. So change in volume per unit volume. Okay, see. So here we have the pressure, the compressive, so the hydrostatic stresses, as I told you before, and it is usually measured at constant temperature. Again, the bulk modulus, or the Helmholtz modulus, is also connected to the Young's modulus with such a relationship: Young's modulus divided by 3 times 1 minus 2 times Poisson's ratio. And again, for materials with Poisson's ratio 1/3, in such a case, B equals E. In other words, if you put here 0.5, so 1/2, at nu, B would be infinite, because that would go to 0, so B would be infinite, so the material would exhibit no deformation. Sometimes it is assumed so. This is one of the models that we sometimes use, but generally the Young's modulus is below 0.5, as we may come back to the table. We see that it's somewhere around 1/3, 0.25. This is the lowest value here. The highest is 0.35. So this is somewhere in between. We can also encounter another problem with thermal stresses, or with some thermal problems dealing with rapid changes in temperature. It can be determined on the basis of so-called thermal shock parameter. And thermal shock, what it is? It occurs when a material is subjected to rapidly changing temperatures in the environment around it. Let's say the situation can occur if, let's say, space vehicle re-enters into the atmosphere. We have a startup of cold automobile engine, or a cold startup of a, let's say, a boiler, turbine, so heat turbine. We have a quenching of metal parts. So there's many situations that the material undergoes very rapid changes of temperature change. Under identical environmental conditions, so the same speed of parameter changes, for example, temperature changes, some materials are more resistant to thermal shock than others. In general, brittle materials exhibit small mechanical strains before rupture, before they break. So the thermal shock can be really a serious problem for such materials. Ductile materials, so those materials which exhibit a lot of plasticity, can withstand larger mechanical strains before the rupture occurs. However, the thermal shock may cause some yielding, so plastic deformations for ductile materials. And the, let's say, resistance to thermal shock can be determined on the basis of the thermal shock parameter, which is shown here. Rm, as I told before, is the ultimate stress. There is a square root of A, which is the thermal diffusivity, as we already defined it. Here we have alpha, so the expansion coefficient, linear thermal expansion coefficient, and Young's modulus. So look at this. A material with high value of ultimate tensile strength, Rm, would be able to withstand higher stress level than the material with, let's say, low ultimate stress. So the coefficient will be bigger, yes? Material with low thermal expansion coefficient would develop smaller thermal strains and correspondingly lower thermal stresses than material that shows a large amount of changes due to temperature change, so higher elongations due to material changes. Again, material with small Young's modulus would be more flexible and able to accommodate thermal strains better than material with large Young's modulus. Material with large thermal diffusivity would tend to develop smaller temperature gradients than the material with small k. So this parameter shows us how fast the temperature equalizes in a material, how fast how rapidly the energy can be conducted into the solid material. So a large value of thermal diffusivity means that energy may, in other words, heat, may diffuse rapidly into the material, and steep temperature gradients, so large temperature changes over small distances, will not be developed. This means that in such case, lower thermal stresses will occur. So that's why the thermal shock parameter will be higher. So in general, the higher the thermal shock parameter, the better for the material. So it's more resistant for rapid temperature changes. Under steady state conditions, the transient thermal properties do not influence the thermal state, so the transient term can be omitted here. This is the thermal diffusivity. So in such a case, we can determine here so-called thermal stress ratio as a material property for use in assessing the material resistance to thermal stresses. So the higher the thermal stress ratio, the better. So the most resistant to material for rapid changes is. So if you, let's say, design a new structure, you develop a new structure, this quantity could be taken into account. And here you have for several materials the magnitude of thermal shock, of the thermal stress ratio, and the thermal shock resistance, thermal shock parameter. Sorry. So the higher the magnitude, the better. This is expected. The thermal shock resistance shows us the magnitude of, let's say, K. So the magnitude of temperature difference which developed in the material would cause damage. We can, let's say, more or less determine in such for such assessment of the material. But generally, the higher the stress, the higher the coefficients, the more resistant the material is. Okay. And now, before we come to determination of the formulas and discussing the thermal stresses exactly, I think we can do a short break, a 15-minute break, and after the break we meet for further part of the information I prepared for you today. So 3:45 we meet again. Yes, are you still there?
Hello, Professor.
Yeah.
I have a question from the previous lecture.
Yeah.
Actually, when we decide to have the thermal expansion and contraction joint, as you were talking about the bridges, then how can we decide actually like the width of the expansion and the contraction joint? Like definitely we have to keep some space with both of the parts of the bridge, and definitely how can we decide that distance?
The distance between to prevent, let's say, destruction. Yes.
Yeah, exactly. For the
We will
expansion and
discuss,
contraction, the space that is actually provided.
we will discuss it.
Oh, okay.
It will be soon, perhaps today even. If not today, but probably today. If we'll not manage to do it today, so for sure next time.
Sure. Thank
Okay.
you.
Okay, we can continue our lecture. Now we'll start to discuss thermal stresses in one-dimensional objects, so in bars. We just let's say easiest case possible, but to introduce the basic relationships, the basic idea. It's a very good object of interest. So, wait, presentation, I forgot. Okay. So, from a basic point of view, stress is defined as a force per unit area on which the force acts. This is the definition you know from your mechanics of material course. And you also know that from the engineering point of view, there are two types of stresses. One is the direct or the normal stress, which I mentioned already. So the force is normal, or in other words, normal means perpendicular to the surface. And the other kind of stresses, or the other component of stress, is the shear stress, which is denoted with letter tau, which is the force that acts tangential or parallel to the surface. Of course, respective stresses generate or develop strains in the material, and the strain is, of course, defined as deformation per unit length, as you can see here. And of course, since we have two kinds of stresses, general two kinds of stresses, we will also have two kinds of strains. One is the directional, or the, let's say, normal strain, which is epsilon. It is shown here. And it can be also treated as a change in length of the material. And the other is the shearing strain, which shows us the distortion of the shape of the material. So the first one is here shown, the strain, the normal strain denoted by epsilon. The other is exactly, this is an angle of deformation, and this is usually marked as gamma and expressed in radians. Because in this case, the shearing stress and strains will not occur, so they will emerge in different, more complex cases of that will be discussed later on. In general, in presence of temperature changes, the strain of a material is generally a function of stress, as we here see, and a function of temperature. If we have the temperature changes, but since we are discussing thermal stresses, so the influence of temperature is observed. We can denote that, resolving it with means of the chain rule of calculus, we may express the differential direct strain in such a form that we have change in strain due to change in stresses, so the mechanical part, while the temperature is constant, and the other part is temperature of strain due to change in temperature. So this is the let's say thermal strain. The first term, as you may remember, several slides back, is strongly related to Young's modulus. Yes, d sigma over dE. So this is a reciprocal of E. And the right-hand side part is devoted to changes in temperature. So E, as it was defined, is d sigma over dE, so a tangent of the angle of the inclination line at the beginning of the stress strain curve. So it can be denoted as sigma divided by the mechanical, let's say, mechanical strain. So it is a strain which is provided by application of force. If you recall the definition of the expansion coefficient, linear expansion coefficient, is 1 over L dl over dt at constant sigma, and dl over L is nothing else as d epsilon. So we have d epsilon over dt, which is here, at constant stress. So the differential can be expressed as d sigma, so changes in sigma divided by Young's modulus, material property, plus alpha times dt, so expansion coefficient, linear expansion coefficient, time change in temperature. So the temperature usually changes from temperature T0, which is the stress-free condition, is usually set as a stress-free condition, so a condition at temperature at which there is no thermal stress. And it is given temperature is reached, so given temperature T is obtained. So if we integrate it, we get sigma over E. This is obvious, this is the mechanical part. And this, what we can see here on the left, is the linear relationship between stress and strain. So in other words, Hooke's law, known from previous stages of your education. And here we have to integrate alpha dt within the temperature range. So starting from T0 and ending up at given temperature T. If alpha is constant, we can treat that as a given temperature range. Alpha is constant. This is very often taken assumption. If the temperature range is not very big, or we don't have particle information about the changes in alpha, we very often assume alpha as constant, as an average within the range, and the epsilon, so along the strain, can be determined as sigma over E plus alpha times dt, so alpha times change in temperature. So this is strain provided by mechanical factors, so force applied, and this is the strain produced by temperature change. So by delta T, you should understand T minus T0, so the T0, where is the mechanical, stress-free condition. If we solve it for stresses, we'll get the stress is E times epsilon. So this is again the mechanical part, minus alpha E delta T. So this part has a negative sign as a compressive stress when it leans against the walls. So a negative stress is usually built there. And now we'll discuss some possibilities of a bar at different boundary conditions. So at different support conditions, how the stresses can change and how the boundary conditions, so the support conditions affect stresses in a bar, and further what we can do to diminish the stress, to release it a little bit. So we'll consider a basic problem of course only at uniform temperature change. So within the entire object, the temperature at a given time shot is exactly the same. So there is no temperature distribution inside the material, neither longitudinal nor lateral, nothing. Everywhere at a given instant of time is the same temperature. And we'll start with, let's say, the most stiff problem, the most rigid, is the bar between two rigid walls, two rigid supports. We have already shown it. Again, this is only showing that we increase the temperature, but generally everywhere we obtain the same temperature at the same instant of time. Of course, it can be heated up or cooled down. We will not discuss the problem of heating up or cooling down, just a given increase in temperature. So let's say at the beginning it was 10 degrees and at the end it was 50. And this is our interest. So we do not discuss how the process ran. We just have the initial and the final stage. So if we do a section, so this is the usual way of solving such problems. So we do a section and try to see what is the stress inside, so what is the internal force, and in consequence what is the force, what is the stress. We can build a equation of equilibrium for the cutoff part of the object. Of course, from here, from the entire object, we can say that RA is equal to RB, but we have no idea how much it is. So this is so-called statically indeterminate problem, because we have only one equation of equilibrium, so for the horizontal direction, for the axial direction, and no information. So one equation, two unknowns, RA and RB. They are equal, but we know none of them. So let's do a section here, and if we get rid of the right-hand side part of the section, we substitute it with internal force N. This is a force which occurs inside the body, inside the material, due to the action of the reaction array. So the equation is the equation of equilibrium is written here. So N is minus RA, but we still know nothing. If we take into account the compatibility equation, so the equation taking into account deformation, we can say that if we allow the object to extend, it would extend by delta LT. But as we see here, in original situation, the object does not extend at all. So let's imagine we compress it with such a force that it will come back to its original size. So the total deformation, which is observed 0, consists of mechanical load and thermal elongation. So mechanical elongation is force times length divided by E times A. This is again what you should know from the basics of strength of material. This is the mechanical. So elongation of a bar provided by force applied. When the material has a cross-sectional area of A and is made of material whose Young's modulus is E. On the other hand, thermal deformation, as we know from today, from the former part of our lecture, is alpha, so the linear thermal expansion coefficient, times length times increase in temperature. And we know that sum of these two is 0. So thermal elongation, which is that much, is balanced with mechanical elongation, so a force with which the object is compressed, and the final result is 0. So we measure 0 change in length because it is not possible due to the rigid walls. So if we compare this, or if we put these two information into the equation, we can say what is the force in the material developed if the material is heated up or cooled down by delta T, and we know the properties of the material. Sigma is force divided by A, so force divided by cross-sectional area. So from here we can say that stress in such a bar is minus alpha E times delta T. And the unit will be, here we have 1 over K, so 1 over Kelvin. Here we have Kelvin, so they cancel out. And the remaining part will be the unit of E. So the same unit as E, the same will be of sigma. If it's gigapascal, will be gigapascal, megapascal, megapascal, doesn't matter. It's still the same. But this is the stress which will be produced at fully constrained bar. So there is no possibility to move. Please look at the thermal stresses problem. Generally, in mechanical stresses, if there are huge forces acting, what we can do to prevent any, let's say, failure, we can make the object bigger, more massive. And in such a case, since we have force divided by cross-sectional area, if the area is bigger, so stress will be bigger, stress will be lower. But here it is not the case. You see, in stress, there is no size. We have only material parameters, and we have increase in temperature. So there is no, the solution is not here. So we cannot make object bigger, and it will be more resistance to thermal stresses. No, this is not the case here. Okay, so we have the first part, the most let's say the most rigid case. So there is completely no possibility to any deformation. Fully constrained object. Now let's look at something different. Let's allow some deformation. Not fully, so it is not completely free, but let's assume that there is a gap. This is what we discussed in the we showed on the bridge. So one of the methods to relax the constraints, the external constraints, is the gap. So it's not fixed, but there is a small possibility to, you see, extend. Either the object is heated or cooled, it has some possibility to change in length, which results that if there is the elongation is governed with the equation we already know, and if the increase in temperature is such that this elongation will be lower than the delta, the gap which is here between the, let's say, a contacting object or a support, whatever it is, we have a gap here. If the elongation is below the gap, so the temperature rise is that the elongation will not reach the boundary, so will not touch the object, the support, stress will be zero. So the object can freely extend. Of course, it may be the temperature rise may be that big that it comes into contact. So in such a case, when the delta LT comes into contact, so would be bigger than the gap delta, we'll obtain deformation, which is delta over L at the contact, before the contact occurs. Okay. So, oops, sorry. So this is the amount of deformation of strain, and it's delta, so the gap divided by the entire length of the object. So this is the elongation divided by the original length. The upper sign plus applies if the temperature change is positive, so we have a rise in temperature, and the lower sign minus refers to the case when we encounter the negative change in temperature, so the temperature lowers down. So since we have here epsilon times E as stress, so stress sigma developed will be E times epsilon, so delta over L, minus alpha E delta T. So as a result of the former equation, the first equation here. So you see that the stress now will be slightly different. We have an opposite sign of sigma and of the mechanical and thermal part. Okay, sorry. I'm looking if there is anybody asking now. Okay, so it can be changed into such a form. Sigma this is the same but a little bit transformed, minus alpha E delta T. As you see, this is the case when we have completely constrained movement. So that would be the maximum stress if no deformations are possible. And here in the bracket we have 1 minus delta over L divided by alpha delta T. So you see that the stress will be generally smaller because we have 1 minus something. If this something is non-zero, so delta is non-zero, the stress will be lower than in the case we have completely constrained deformation. So you see, you can, let's say, influence the amount of stress, the magnitude of stress developed in such a system if you provide a thermal gap here, a gap which is for thermal expansion. Okay, so this is one of the possibilities to reduce stresses. So what happens? The material, even if it is the case, the material up to certain amount extends without stresses, and just at the moment when it encounters a resistance, so it comes into contact with the support, this is the onset of developing stress. So part of the delta T was used for, let's say, stressless deformation. So only a part of the delta T will provide interaction between support and the object. So in general, stresses will be lower, and you see the bigger the delta, the lower the stress. So one possibility, and it is very often used, as you saw, as an example of the bridge. Other possibility, instead of applying a rigid support, we can apply a, let's say, elastic support. So we allow slight deformation at the support. It is here schematically marked as a spring here. So it's a spring element, means it must not, it is not necessarily a spring applied there. It must be, it may be a material that is elastic. It may be what it may be else. Yeah, material that is elastic. So the support exhibits some elasticity. So it deforms under the extension. So the invasion of the material, of the extending material. So the story is similar as before. We have a bar of length L, whose temperature is changed by delta T. One end is fixed. On the other, we have a spring element. The coefficient, the spring constant, is K_, so K spring, and you may remember that force developed by a spring is proportional to the spring element and to the elongation of the spring. So the total change in length of a bar is epsilon times L. And this epsilon consists of sigma over E, so the mechanical one, and alpha delta T, of course, both multiplied with L. The spring force, as I told you, is proportional to the deformation. If we have the initial condition, so let's say we have at the T0 temperature, the spring is free, so it's in this stress-free longitude. So there is no force inside. It's in its natural length. So it is neither extended nor compressed. So it's free, completely free at t equal to 0. So force generated by this spring equals to 0. When we start to heat it up, in this case, the spring starts to be compressed. Yeah, the object will elongate, the bar will elongate, and so the spring will be compressed. So it will be, the length of the spring will be changed, and it will generate force. So spring force is the spring constant, K, times elongation. So this is a compressive force. If the bar compresses the spring gives up the same, so compresses the bar. So it will produce a negative force in a bar, so compressive force in a bar. The same story as it was with the rigid wall. In the rigid case, in the rigid wall, there was RA or RB, so the reaction, full reaction. Here, the reaction is proportional to change in length, so to the delta L. And we know that from definition that this is sigma times A. So this is stress developed times cross-sectional area. So if we put it there, we'll get minus sigma A over K spring equals sigma LE plus alpha L delta T. Okay, so here we have sigma, here we have sigma. If we solve it for sigma, the solution will be minus alpha E delta T, and again, this here at the numerator is stress for the case when we have rigid walls, and here we divide it with 1 plus something, and this something releases the stress, relaxes the stress, so diminishes it. 1 plus E times A, so Young's modulus times cross-sectional area, divided by K spring times L. And here we can see how we can affect the stress in the system for this case. So if the spring constant is 0, so let's say there is no spring, this is infinity, which means that stress is 0. It is as the object is not constrained. So this is the same story. There is a gap and it can freely expand. If, on the other hand, if the spring constant is infinite, so very, very, very high in boundary as a limit, the infinite magnitude results that we have a rigid wall here, exactly. So that will be 0, and stresses will be equal to those stresses which occur at rigid walls. Okay, so you see how deep you can change stresses, how deeply you can relax the stresses, changing the spring constant. So the stiffer it is, the bigger the stress will be here. So you can adjust, you can design a system for a certain amount, for example, of stress. So allowable stress is on set level, and you can say how stiff the support should be to achieve stresses at given level. Okay, so let's do some examples to show how it works, how much we can achieve here, what's going on. So we have a 100 millimeter nominal pipe in a system. The pipe's outside diameter is 114.3 and the wall thickness is 6 millimeters. So you have information about the geometry of the pipe. The length of the pipe is between supports is 2.54 meters. The pipe material is a chromium molybdenum alloy steel having the following properties. Rm, so the ultimate stress is 400 megapascal, yield stress is 270, Young's modulus is 200 gigapascal, and alpha, so the thermal expansion coefficient, is 12.5 times 10 to the minus 6 power, 1 over K. We know that the allowable stress developed in the pipe must not exceed 100 megapascal. The pipe is initially stress-free, so at the beginning, between the supports in the pipe there is no stress, and this is in temperature 20 degrees Celsius. Finally, the pipe is heated to a uniform temperature of 200 degrees Celsius. So it's heated up by 180 Kelvin. The question is, we should first determine thermal stresses if the pipe is rigidly fixed at each end. So the first case, it cannot deform at all. Second, what gap size would be required to limit the thermal stress to 100 megapascal? So we know that the allowable stress is 100, and what should be the gap size? That the stress is limited to 100 megapascal. And the third case, if a bellows joint were used, so elastic joints at the end are used as the spring element, what should be the constant of a spring that would be required to limit the stresses to the 100 megapascal? So we may encounter that for the rigid case it will be more than 100, and we have to reduce the stresses to 100 megapascal. Once by a gap, in the other case by application of bellows joints with appropriate spring constant. And we'll see what we can achieve in this situation. Okay, so this is the first case. This is what we have discussed. Now we will have some numbers. We'll see what magnitudes of stresses we can achieve in real situations. We see that this is not very huge thermal gradient, so change in temperature. Because if you take, for example, elements, let's say piping system in a power engineering boiler, you'll see that at, let's say, out of operation stage, the temperature may be something like 30-40 degrees Celsius. Let's say in a power plant there is quite hot at the machinery room, and while working the temperature rises to 800-1000 degrees Celsius. So you see the heating up is really high. We'll observe what happens if we only heat it up by 180 degrees. So rigidly fixed pipe, we know that the stress, normal stress, is minus alpha E delta T. We have everything to be able to calculate it. So if we put the data in, we have 12.5 times 10 to the minus 6 power, 1 over K, 200 gigapascal, so it is 200 times 10 to the third power megapascal. And the temperature rise 200 minus 20 in Kelvin. Kelvins cancel out. The result will be megapascal, and we obtain minus 450 megapascal. Okay, we can see this is a chromium molybdenum alloy steel. If we go to our table, do we have something like this? It's somewhere here. Or this one. It's somewhere here. So the ultimate stress is something around this value. So we can expect that the material for sure is within the plastic range, so is above yield stress, or even reach the ultimate stress level. So this is a destructive temperature rise for this material. And this is, as we see, this is only 180 degrees Celsius temperature rise. Okay, so, but the ends are fixed, so no movements are possible. So let's look what we can do with the problem to reduce the stresses a little bit. Assume we have a support with gap. So there is a gap delta before it before it gets into contact with support. So we know that the stress is governed with such a formula, which we already developed, and the gap is here. Other parameters we know the maximum stress available, so allowable stress. We know alpha, we know E, we know delta T, and we know L. So everything is given. So this data is introduced, and we can calculate delta from such a formula. So if we solve it for delta, we can calculate the gap here, which is 4.45 millimeters, which means that if the gap between our bar and the wall will be 4.45, the stress developed will not exceed 100 megapascal, because if we limited this to 100 megapascal, it's the allowable value given here. Okay, we can check also the pipe against a buckling, because if it leans against the wall, it is compressed. As you may remember again from the strength of material course, a slender object, so long and thin object exposed to compressive loads are threatened with buckling process. So a sudden loss of stability. So it can buckle, it can rapidly bend if force, a compressive force, is bigger than so-called critical force. Recall the basics of strength of material. So for this reason, we will need the cross-sectional area of the pipe, which is A times D minus G. G is the thickness of the wall times G, and it will be at 2041 square millimeters. So this is the cross-sectional area of the pipe in question. Compressive force in the pipe will be, as we know that the stress is 100 megapascal and we have the cross-sectional area, the force that compresses the pipe in such a case is 204 kilonewtons. Okay, to assess to check the pipe against buckling, we need some more things. This is the moment of inertia, which is for this case for a pipe over 64, the external diameter to the fourth power minus d minus 2g to the fourth power. So external pipe minus external pipe. So this is that much. This is the moment of inertia, and the Euler critical force is pi squared times E times I divided by the buckling length squared. And it is, as we put there, 1837 meganewton. So this is the force that would provide buckling. This is the critical force. Our force is 0.2 meganewtons. Was 204 kilonewtons, so it's 0.2 meganewtons. We see that the force is like 9 times lower than the critical value, so there is no threat of buckling. So we can sleep calmly, no problem with the buckling in such a case. So this is the thing. This was the possibility to reduce stresses if the gap is introduced 4.45 millimeters. So that was one solution to the problem of excessive stress. We can check, or there is also check what size would be required to have no stresses in the bar, which means how far the object extends. And this is the amount, of course. Sigma is alpha L delta T. And it would be 5.72 millimeters. So if the gap was that much, the pipe would not come in contact with the support. So there would be no stress at all. To have stresses not bigger than 100 megapascal, it's enough as the gap is 4.45 millimeters. So you can, as you see, you can control the amount of stresses generated, developed in the system, while applying appropriate gap between object that is extended, that is under the change temperature condition and the support. And there was a second possibility to be discussed. There was such a question: what a elastic support should be applied there? So what should be the spring constant? So in other words, elasticity of the support to have also stresses not bigger than 100 megapascal. So this is the case we have to discuss now. So at one end there is a elastic support, which is marked here as a spring. And the question is, what should be the K spring to relax the stresses to 100 megapascal, from this 450 at the rigid case to 100 in the elastic support case as well. So we use the formula also developed there. So we have minus alpha E delta T, and the factor which is responsible for relaxing the stresses, so this part, EA K spring alpha. All of these data are determined. We have to solve it for K spring. So determine how big the K spring should be to have the stresses not that much, not bigger than 100 megapascal. So if we divide it by alpha E delta T, so we have on the left hand side sigma divided by E alpha E delta T, and that is minus 0. And the minus also on the right, this is minus 0.0222. On the right hand side we have 1 over 1 plus EA K spring L. So calculating K spring, or at first this factor which is in the bracket, it should be 3.5. So the K spring should be 45.9 mega newtons per meter, which means that 45.9 mega newton force would provide a meter change in length. Of course, this is expressed in the basic SI units. If you divide it by 1000, so here would be kilonewton, here would be millimeter. So 45 kilonewtons of force would be required to compress the spring by 1 millimeter. So this is the meaning of the K spring of the K. So this is 45 meganewtons per meter, and this is fairly stiff spring. And typically commercially available pipe bellows, so the fittings, the elastic fittings at the ends, with for let's say 100 millimeter pipe would be about 0.05 meganewton per meter, so about 100 times lower than this amount. So quite a stiff spring would be enough to obtain stresses at the level of 100 megapascal. Okay, if we apply, so let's say commercially available bellows with a constant 0.4 meganewtons per 0.44 kilonewtons per millimeter, it would require with a stress like one and a half megapascal, so it would drop rapidly. So we don't need very much very elastic springs to reduce stresses significantly. So this is the second possibility, and a very important possibility, to relax stresses, which is very often used in practical applications. So two possibilities. One is thermal gap, expansion gap. The other is elastic support. The worst case is, of course, rigid support, so no possibilities to movement, provide huge stresses, and if the temperature rises big, it can easily provide destruction of the system. So this is very important from the point of view of many components that are exposed to high temperature changes during its operation, during, let's say, out of service time and normal operating condition states. So this is an important problem which has to be focused and which has to be solved. Okay. Now we'll go a little bit deeper. We will look at problems that we have components co-working together. So let's say we have bars in parallel. So there are two objects, which is very often the case also encountered. Different structures are built in such a way that we have elements that are connected together. And we will discuss here such a problem that we have bars in parallel. They are of different lengths. This is just schematically shown that they are one next to another. The configuration can be different, but in generally they work together. So the first one is of length L1, the other is of length L2. The left ends are fixed, and the right ends are joined together, so with such a rigid plate. This gray rectangle here means that this is a plate which is rigid, meaning that the plate does not deform. It can move left, right, together with the bars, but it cannot deform. It cannot bend, or any other deformations are not possible here. And what will happen if bar number 1 will be heated up by delta L1, delta T1, and the second bar will be by delta L2. So both bars at the beginning are at stress-free conditions. So T0, both are at temperature T0, and there is no stresses, no interaction, nothing. They are perfectly adjusted one to another. And then at some moment they are heated up. The first one up to temperature T1, the other one up to temperature T2. They are generally different. And at the beginning, 0 force, there is no force applied. So at the initial condition. So as you see, they are constrained here. They can, let's say the temperature rises, so the bars extend. They deform, they do extend. So one will try to extend more than the other, depending on its initial length, depending on the properties of the material, so expansion coefficient, depending on the temperature change. So one will try to extend more, the other will try to constrain the movement. So they will interact between each other. So delta L1, so elongation of bar number 1. Yes, on the basis of the formula we have developed the beginning of this part is sigma over E, it's epsilon times L1. Yes. So this is the elongation due to a mechanical part and elongation due to the thermal expansion. And we know that the system, so the plate, cannot deform, so it will travel together. It is still connected to the bars, to both bars, so their movement provided by one bar will try to pull the other bar and opposite. So it will travel by the same amount, looking from the point of view of the first bar or looking from the point of view of the second bar. So this is the total elongation of the system. So it is exactly the movement of the plate, delta L0. It can be treated like this. From the point of view of the second bar, it is the same story. Sigma 2, so sigma develops, stress developed in the material, its length and its Young's modulus, plus alpha L delta T. And it must be the same delta 0, because they travel together. So if we compare these two expressions, but first we provide a force balance. So force applied here and forces exerted by the two members are to be 0. So in other words, F is sigma 1A1 plus sigma 2A2. So external force is equal to force generated by bar number 1 and bar number 2. Sigma 1A1 is, from these formulas, we can derive it from this formula, sigma 1 and multiplied with A1, it's E1 divided by L1 times delta L0 minus E1 A1 alpha 1 delta T1. This is exactly force in bar number 1, because sigma times A is force. The same for the second member. From here, we can determine sigma 2 and multiply it with A2. So this is A2 E2A2 divided by L2 times delta L0. This is the total elongation of the system, minus E2A2 alpha 2 delta T2. And force, if we apply it, put it into the force formula, it becomes something like this. E2A2 divided by L1, so with 1, everything with 1, EAL, EAL for the first bar, for the second bar. Since they travel together, so the delta L0 is common. And here we have the force generated by the temperature change. So delta L0 can be found. Oh, there is one thing missing. Sorry, there is one thing missing. I lost this force, F. The force should be here plus P. I'll change it now because I'll forget in a moment. So plus F. Okay, we're back. So if we calculate the delta at 0, so how far the system deformed, so how it moved, the plate that joins together these two bars, how far it moved, it's delta at 0, and it depends on the materials of both components, E alpha, on their cross sections A, on their temperature rise, and here we have the same components. Okay, and of course it depends on the external force, if there is any. If there is no force, that would be 0. If mechanical force is applied, as on the picture, we have additional F. So sigma 1, going back to the formulas at the beginning, introducing the delta L0, it's sigma 1 is E1, so Young's modulus for the first bar, alpha 1 delta T1, so this is the thermal stress, and this is the, let's say, mechanical stress, so stress resulting from interaction between these two members. One tries to push the plate, the other keeps it back. So there is a mutual interaction between these two components. So this is delta L0 to delta L1. So to what extent the material deforms to its original length, and similar thing for the second member, minus E2 alpha 2 delta L2 minus delta L0 over L2. We see that they have opposite signs, because if one of them extends more than the other, it will be constrained by the other. So let's look at this. If the object number 1 is heated up higher, it wants to move more than the object number 2. So it pushes it strongly, but that one constrains the movement. So interacts with a force opposite. So this force tends to compress the member, so generates a compressive stress here. On the other hand, action, this extension of this member, try to also extend this member, so generates a positive tensile stress in the second object. So depending on the magnitude of delta T, but in general, it will always be the same story, that one will have a positive stresses, the other will have negative stresses. So one will be extended by the other, and the other will be compressed by his neighbor. And this is the result. So if we put the delta L0 here, the final formula can be expressed in such a form. It's minus E1, so E for a given material. And here we have, you see, let's say forces for generated by temperature of one on the second object, influence of the mechanical force if something like this is applied. So you see they are very common. The formulas are very common. You see here is alpha 1 delta T1 and alpha 2 delta T2 and the ratio of lengths. Here is opposite. Alpha, the actual member, this one we calculate, minus his neighbor, and again ratio of lengths. Mechanical part, that's an action of the force, external force. If no force is applied, the factor will be cancelled, so it's 0. And here we have a ratio of rigidity of these members, so E times A, and length and ratio of lengths. So on this basis we can determine stresses in both members, and we see there is a mutual interaction between them. Stress F2 or shortage can be calculated as F over A2 minus sigma and interaction between these two objects. So from the balance equation, as we have the quite beginning, where was it? From here. Okay. If we have more than 2 bars, so a general case for n bars connected in parallel, elongation of the entire system, so change in length in the entire system, is external force if applied, if not applied, F is 0, plus, and we sum up such factors: Young's modulus, cross-sectional area, expansion coefficient, and rise of temperature. So we sum up such factors for all of the members, and we divide it by sum of such terms EA divided by L. So that it's quite general formula for this problem. Stresses in such a case would be E for particular member alpha delta T minus delta L0 over length of this actual member. So for each member we can calculate separately this magnitude of stresses, and the L0, which is here, can be calculated from the above formula. So you see, you can even make a computer program to calculate stresses in many bars. If you have the parameters, you have its actual working conditions, you can calculate quite easily, generally, the stresses and elongation of these of the system. Okay, and some examples. Titanium sleeve with the aluminum core. So inside we have an aluminum core. Is closed with two rigid covers. Again, rigid covers, they cannot deform. Assuming that at the reference temperature, so the starting temperature, the elements are free from stresses. So they are perfectly fitted. So no stress is generated at, let's say, the initial temperature. The question is, what will be the stress in the elements, and what will be their elongation if they are heated by 100 Kelvin. Here we have the material data. So this is a cross-sectional area. This is the, let's say, a sleeve, and inside there is a core, aluminum core. So this is made of titanium with following parameters. Alpha is 9 times 10 to the minus 6 power, and Young's modulus is 110, and cross-sectional area is 100 millimeters squared. Inside we have an aluminum core with cross-sectional area 120 millimeters squared. Alpha is 23, so you see a huge difference, 2.5 times. And we have different Young's modulus for aluminum is about 70 gigapascal. And we have to calculate first stress in the elements and then their elongation. So if we do a cross section, we'll obtain at the internal, we can see the internal forces. So this is the internal force in titanium sleeve and force in aluminum. And these two forces, since it's in equilibrium, sum of these forces must be 0. Of course, I shouldn't have do it like this because it's a circle, it's a pipe, so both forces have to be shown in the center, but it will be hardly visible. But the titanium also should be here in the center. It should be Ft just in the center. But the result is exactly the same. So half of force here, half of force here, and the cross section can be also treated in this way. So equation of equilibrium is the sum of these forces is 0. The result is that Ft is equal to minus Fa. None of them is known. So we know we should also spot from the previous examples that this is a statically indeterminate problem, and we have to have the geometry of deformation equation or the compatibility equation showing us the deformation. And we know that since these two materials are connected together, one is inside the other, so they work together, they deform together. So deformation, displacement of titanium are the same as displacement of aluminium. They have to travel together. And we know that deformation, the elongation, is provided with force, and is provided with temperature change. This is what we are talking about all the time. So force in titanium provides elongation. So force times length divided by ETAT. So the mechanical elongation, and the thermal elongation alpha L delta T. Same stories for aluminium, for the core. Force which is developed inside times L EAAA plus thermal deformation. And both are the same, so we can compare them together. So they are put into an equation. And we can determine the force. So from equation of equilibrium, Ft is equal to Fa, so we can substitute one of them. And can calculate any of this force with a difference of coefficients of thermal expansion. We have a common increase in temperature, and here we have cross-sectional areas and Young's modulus, so such a factor. All of the data are known, so we have the expansion coefficients, we know how much it was heated up, and we know all the material and cross-sectional parameters. So if we put the data in, we'll get the result. So the force developed both inside the aluminum core or the titanium sleeve is the same and is equal to 6.66 kilonewtons. So as you may expect, the sleeve will be extended and aluminum will be compressed. If we look again at the, if the core extends more, it will be constrained by the titanium sleeve. So the titanium sleeve will provide a compressive force on the aluminium, while the aluminium will provide a tensile force on the titanium. And opposite. So one is compressed, the other is extended. We know the magnitude of the force is 6.66 kilonewtons. We were asked to determine stresses there. So stress in titanium is the force divided by cross-sectional area of the sleeve. So it is 66 megapascals. In aluminium, it is minus 55 megapascal. So you see the stresses in both components, and it will always be opposite. If one is in tension, the other will be in compression because they interact between each other. So they deform in a different rate. The total elongation is the same AT or UT or UA, both deform the same. And if we put the data into the formula, we'll get that 1.44 millimeters will be observed, the deformation of the entire system, while it is heated up by how much was 100 Kelvin. So, but if there is more than one material involved, it results in mutual interaction between these two, between these materials, and there is, let's say, we can say that this is somehow internal constraint, because everything happens inside the materials, co-working, co-making components. Okay, one more example. We have two stainless steel pipes. The external pipe and the internal pipe. Both have the same parameters, so alpha and E. Length of the pipes is 5 meters. They are concentric and they are attached at both ends. So this is closed with, let's say, a plate at the ends. They are joined with the plate, so they cannot detach. The inner pipe is 100 millimeter nominal pipe, so similar as it was in the previous example. Outside diameter is 114.3 and wall thickness is 30.5 millimeter. The outer pipe, denoted as number 2, is 150 millimeter nominal pipe, whose outside diameter is 168.3 millimeter, and the wall thickness is 3.4 millimeter. We know that maximum allowable stress for the material is 130 megapascal. And we also know that both pipes are initially at stress-free conditions if the temperature was 20 megapascal. And suddenly the outer pipe is warmed to 25 megapascal. So only 5 temperature rise. Determine the lowest temperature to which the inner pipe may be cooled by a liquid flowing through, such that the design stress level is not exceeded. And we have the design stress level as 130 megapascal. So this is the, let's say, allowable stress. There is no external force applied to the ends of the pipe. So we have very similar situation as it was previously. Previously we had a filling inside, now we have 2 pipes. To be honest, connected in parallel, one into another. So let's say it may be a shield, the external pipe may be a shield. Inside there is the main pipe which transfers fluid, let's say cold fluid if the temperature, external temperature is not big. So we let's say make a shield against heating up the, let's say, cryogenic fluid inside, for example. So we have all the data for geometry and material data for both pipes. We know that they are connected together at both ends, so they cannot detach. We know their maximum stress, which is allowed. And we know that during operation, the external pipe heated up from 20 to 25. At 20 degrees, when both pipes were at 20 degrees, there were no stresses. And we have to determine how cold the internal pipe may be before the stress, the maximum stress, the 130 megapascal stress, will be exceeded. If the external pipe is heated a little bit by 5 degrees. So we have exactly the situation which was discussed before. We have two pipes in parallel, so we can use the formulas which were developed there. So we need to look at the formulas. We have stresses here, so we need delta T's. One of them will be calculated. We know stresses which can be developed. There is no force, so this factor is 0. And we have such products EAL. So we need to have cross-sectional area. So cross-sectional area of the first pipe is 1066 millimeters squared, and the second pipe is 1761 millimeters squared. And this ratio E1A1 L2 divided by E2 A2L1, it is in the factor. Since we have the pipes made of the same material and the same length, so E1 and E2 is the same, L2 and L1 is the same, so it cancels out, and there remains only the ratio of the cross-sectional areas. So it's 0.6052. This is the ratio of the cross-sectional areas. What else do we need? We have a temperature differences. The delta T1 is T1 minus T0, and we know that. And delta T2 is T2 minus T0. T0 is known in both cases. T1 is known. No, T2 is known. What happens with the external pipe? So it's hit by 5 degrees. But if we expand it, we'll get T1 minus T2 from this difference of temperature changes for both pipes. So it is T1 minus T2. So the final temperature of pipe number 1 and final temperature of pipe number 2. So sigma 1, if we introduce all the data in, is E1 alpha Q1 minus T2 divided by 1 plus A1 over A2. So the temperature difference calculated from here is sigma 1, which is the elbow stress. We try to find out what should be what can be the temperature difference for stresses that are set at 130 megapascal, and the remaining data is given as provided. So the temperature difference between these two pipes can be, if we put the data in, 71.2 minus 71.2. So the lowest temperature of pipe number 1, so the pipe that is inside, is 25 minus 71.2, so it's minus 46.2 Celsius. And in such a case, sigma 2 will be 78.7. So what we gained, that if the temperature of the external pipe has risen by 5 degrees Celsius, so it's 25 now, the internal pipe temperature may be as low as 46.2 megapascal, minus 46.2 degrees Celsius. And in such conditions, in this pipe number 1, the internal pipe, stress will be 130 megapascal. But on the other hand, in the external pipe, stress will be positive and it will be 78.7. So it's half of the, let's say, a little bit more than half of the stress which is obtained in the internal pipe. Okay, and some remaining parts I think we will be able to finish this topic today. I don't know, we'll see. So the same situation can occur, similar as it was for a single member. We can have the same situation in case of, again, two members connected together, but not rigidly, not with a rigid plate, but providing them a slight independence. So we can again apply there a expansion gap. So they are not fixed together, but there is a slight a possibility of slight difference in elongation. So between they get into contact, there is let's say some buffer available. So looking at this situation here where we have a gap, so these two members, previously they were connected with a one plate, rigid plate, so the ends moved together. Now they are, let's say, connected with a pin. The pin is fixed with the lower bar, and there is a gap in the upper one. So you see that if either the upper changes a little bit, extends or contracts, or the lower changes, to some amount of deformation, the objects will not be in contact unless until the deformation reaches the magnitude of delta. So a very similar thing to the previous case, to the case with a single member only. So this is the deformation of member number one, so elongation or changes in length by member number one, quite obvious already, alpha 1, L1, delta 2, 1. and elongation or compression of member number 2. And if they will not come in contact, so if the actual gap size is greater than the critical gap size, the bars are actually unconstrained. So their thermal constraints is 0. And we can determine the critical gap size would be a gap size for which the 2 bars begin to move as a unit, so together. So delta L1 is delta L2 plus the sigma critical. So this is when these 2 members come into contact and will be moving together. So the critical gap size would be a difference between these 2 deformations. Okay, elongations of these 2 members. So it depends on the materials, length of both members, and their rise or decrease in temperature. So if the actual delta is bigger than the critical one, they will not come into contact. So this situation never occurs that they come into contact, and stresses will be all the time 0. If the actual gap size is less than the critical value, the bars will be partially constrained. So to some extent they will deform without stresses, but finally they will come in contact and the remaining part of their journey will be together. And we can have plus or minus here, of course, depending on which one moves faster than the other. So if the formation of member number 1 is bigger than member number 2, it will be plus. If opposite, it will be minus. So we can express it in such a way as previously. So this is the known formula. Delta L1 is the mechanical loading and the thermal loading. Once more, the mechanical loading can be as a result of their common interaction between these 2 members, and that will be the length, the change in length of the entire system. This is the overall displacement of the system of bars, and here we have plus minus the delta, which is between these 2 members. Again, the sign here plus applies when the thermal expansion for bar number 1 is greater than the thermal expansion for bar number 2, as it was marked previously. And delta L2 is, of course, the same story. So mechanical part and thermal part, and this is the delta L0. So the gap is involved here. And there's one gap between these 2. And if we solve these 2 equations for stresses, so firstly we of course applied the sigma 1 A1, so multiplied the same operation as it was previously provided. So sigma 1 calculated from here and multiplied with A1 because it's a force. This is from member number 1 and from member number 2. And let's now consider the case in which there is no external load applied. So we have only mutual interaction between these two members. So net force, external net force is 0. Yes, there is nothing else acting from outside. So only if one member extends more, drags the other member. So they interact between each other, so with the action-reaction. No external force applied, so sum of these two forces generated must be 0. So if no general force is applied and 0, we have that if the lower member extends more, it will drag the other member, so it will provide opposite force in the other. So the equation for equilibrium is F1 plus F2 is equal to 0. These are the factors that are on the previous slide. That's why we found for these forces F1, A1. So this is force in member number 1, and this is force in member number 2. Sigma times E is just a force. So if we put the data in, the L0, so the sigma times A from previous slide, yeah, it gets bigger and bigger. So the formulas are starting to be terrifying, but in general there are some only mature properties, lengths and rises in temperature. And here is the delta observed, which is the gap, the thermal gap between these members. So the total elongation of the entire system, when it gets into contact and they move together, can be expressed with such a, let's say, quite a big formula, but still analytical formula. We have E1, A1, alpha 1, delta 2, so everything for member number 1, same for member number 2, divided by the rigidity divided by length, and plus or minus, depending on the direction, E1, A1 over L1, the same factor, times delta, and divided by the same factors, sum of these two factors for both members. So in consequence, stress in member number 1 can be calculated very similar to the way we calculated with the members without thermal gap. The only difference is here, delta over L1. So we see that with this factor we can diminish stresses. If one of the stresses diminished, the other is also diminished because it is influenced here by delta 0. So the mutual journey of these two members is smaller. And okay, so I think because there is only a couple of minutes left, so I think we'll come back to the topic next time. We'll discuss the problem on the basis of example showing us the influence of the gap, and we have to finish also. We have to also introduce one more thing, which was discussed for a single member. That is the elastic connection between members. and that will be also here introduced, and we'll also illustrate it with an example, and we'll see how the connection influences the members, to what extent let's say the kind of support of the connection can affect stresses, to what extent they can be reduced when we apply a certain gap, expansion gap, or we apply a certain elasticity in the connection. So I think it's quite a lot of material for today. I'm aware that there are some terrifying formulas occurring here. Of course, you don't have to remember that. I'm just showing you the way of solving the problem and the influence on different kinds of supports, which are very important, on the stresses which are generated, developed in the system, and how we can contradict these stresses, how we can relax the stresses, what to do, and what is important in designing such a systems where the thermal stresses are involved. And next time when we will discuss the problem on examples, that will be, I think, it will get a little more clearer. Okay, do you have any questions? Would you like to ask something, or you have enough for today and we'll meet next time?
I think that we are quite overwhelmed, so.
I think, so do I. Yes, there is a lot of material, and there is a lot of formulas which have to be thought over, and so I think it's overwhelming material. So please don't be afraid. It's just let's say some informative knowledge. If anyone will require this, deepen this knowledge, we'll have to go back there and study it more thoroughly. But now this is, let's say, I would treat it as an informative lecture, about a general lecture about thermal stresses. Okay, if you don't have questions, thank you. If anyone wants to ask for something, please. If no, so thank you.
Thank you.
Thank you, goodbye.
Bye, bye.
Thank you. Bye.
Bye.
Thank you so much, Professor, for such an informative lecture. Thank you so much. Bye.
Thank you so much.
Oh, I see this information that we should stop at 5. Really, you are yeah, yep, that's true. Sorry.
Yeah, it's okay, no problem.
Sorry. Next time we'll repair this.
Yeah, sure.
Okay.
That's okay. Have a good day. Bye.
Bye.
I have one question, Mr. Professor.
Yes.
I don't know because I must leave our meeting and connect again. So I don't know if this was mentioned. How I can pass